Finding the equilibrium concentration when Ka or Kb is given. This is a brand new concept that was not introduced in the equilibrium chapter. Calculations involving equilibrium are not accurate, and a 5% error is acceptable. The quadratic equation must be considered, but it can be avoided if the assumption check is greater than 500. What is the assumption check? Well, in the assumption check, if we take the initial concentration that is given and divide it by the Ka or the Kb, depending on the question, and if that is greater than 500, then one can assume that the x value in the denominator is negligible. Again, the x value in the denominator is negligible, meaning we can get rid of the x, but only in the denominator, not in the numerator. The best way to show how this question works is to go through an example. Example 7. Calculate the equilibrium concentration of hydronium ions in a 0.56 solution of HClO2 if the Ka of the solution is 3.5 times 10 to the negative 6 molar. Well, we're looking at a 0.56 molar solution of HClO2. HClO2 is a weak acid, and the concentration given is not directly at equilibrium, therefore we must use an ice table. So as before, the beginning of this question is no different. HClO2 plus H2O, equilibrium arrows, ClO2 negative plus H3O positive. The negative sign there. We set up our ice table. Water still not included, it's still a liquid. The initial concentration is 0.56. We start off with no products. We always lose reactants, we gain products. And the equilibrium line is the first two put together. We have been told that the Ka of the solution is 3.5 times 10 to the negative 6, so that's still our extra piece of information that we're looking for. So we can set up our Ka expression. Ka is equal to ClO2 negative times H3O positive all over HClO2. And now we plug in what we know. We know that the Ka is 3.5 times 10 to the negative 6 molar. We know no other information, so for the equilibrium concentration of ClO2, we put in X. For H3O positive, we put in X. And for HClO2, we put in 0.56 minus X. And at this point, you'll notice that we have an X in the denominator, and we must do our assumption check at this point to see if that X in the denominator is negligible. And if you go back through the examples that you've done throughout this booklet, you will notice that most and many times when we go to find the equilibrium concentration of the reactant, X is so small that the initial concentration did not change at all anyway. So our initial concentration, so our check is our initial concentration over our Ka. Our initial concentration here is 0.56. Our Ka is 3.5 times 10 to the negative 6. So we do that out on our calculator, and it comes out to be much greater than 500. And when it comes out to be much greater than 500, this makes us super happy because we do not need to use the quadratic formula. So again, when it comes out to be greater than 500, it means that the X in the denominator is negligible. Therefore, we can now rewrite this as 3.5 times 10 to the negative 6 equals x squared all over 0.56. This now makes it much easier, as you will notice that we can cross multiply so we can eventually isolate the variable. When we cross multiply, we will have x squared equals 2.0 times 10 to the negative 6. In order to get x by itself, we must square root both sides. So we will have x is equal to 0.0014 molar. Realize that when you take the square root of a number, you will get the positive and the negative values. However, in a real world case, it would not make sense for us to have a negative concentration, so you can automatically disregard that one. Going back to the question, it asked us, because at this point you've probably forgotten, as I have, we've been asked to calculate the equilibrium concentration of the hydronium ions. If we go and look at our ICE table, we said that the equilibrium concentration of the hydronium ions was X, and we have just calculated X. Therefore, the equilibrium concentration of H3O positive is 0.0014 molar. Example 8. Formic acid is a moderately weak monoprotic acid with a Ka of 1.8 times 10 to the negative 4 molar. Find the hydronium concentration in a 0.0010 molar of formic acid. Well, for formic acid, if you're not sure what the formula is, you can look it up on your acids and bases strengths table. HCOOH. We will react this with water with equilibrium arrows to give us HCOO negative. Notice that the proton donated was the last one, and H3O positive. We were told that we had a moderately weak monoprotic acid, that being formic acid, and we were asked to find the hydronium concentration given a 0.0010 molar solution. So we will set up our ICE table. Water, of course, not included. Initial concentration 0.0010. We always start off with no products. We lose reactants, we gain products, and the equilibrium line is the first two put together. Hopefully by now, the ICE table is second nature to you. Our extra piece of information was that the Ka was 1.8 times 10 to the negative 4, so we can set up our Ka expression. Ka is equal to products over reactants raised to the power of their coefficient. And at this point we can plug in what we know. We know that the Ka is 1.8 times 10 to the negative 4. We know that the equilibrium concentration of HCOO negative is X, hydronium is X, and formic acid is 0.0010 minus X. At the point where we have a variable X in the denominator, we must perform our check. Our initial concentration over our Ka value. Our initial concentration here is 0.0010. Our Ka is 1.8 times 10 to the negative 4, and we want this to come out to be greater than 500. Unfortunately, this only comes out to be 5.6, which is less than 500. And this is going to make us very, very sad, and now this video very, very long. It does mean that the X value in the denominator is not negligible. It does have an impact, which means we cannot get rid of it. So we need to go back to our original setup, and we must now cross multiply. When we do, we're going to get, I'm going to start down here, x squared. So 1 times x is x squared. And 1.8 times 10 to the negative 4. outside of 0.0010, subtract x. In order for us to get this into the brackets, we must, in essence, FOIL it in. So we are going to get x squared equals 1.8 times 10 to the negative 4 times 0.0010 will be 1.8 times 10 to the negative 7. And then 1.8 times 10 to the negative 4 times negative x is minus 1.8 times 10 to the negative 4x. Now we're getting very, very close to a quadratic formula. We just need to bring everything over to the one side and order it so that we will have a, b, then c. So we have x squared plus 1.8 times 10 to the negative 4x, subtract 1.8 times 10 to the negative 7 equals 0. And it is at this point that we are going to use the quadratic formula. The quadratic formula is given to you on your data sheet for Chemistry 3202. And it's x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Knowing that a is what's ever in front of the x squared, b is what's ever in front of the single x, and c is our constant. So this is a, b, and c. Knowing that, you can now plug it into the quadratic formula. So we have x is equal to minus 1.8 times 10 to the negative 4 plus or minus the square root of 1.8 times 10 to the negative 4 squared minus 4a, which is 1, c, which is negative 1.8 times 10 to the negative 7, all over 2 times a. At this point, since this is a chemistry question, the number of steps for you to solve this mathematically is completely independent and personal. You will not be marked on the number of steps it requires for you to get to the final answer. You'll simply be marked on the math that you complete. For instance, if it takes you 3 to 4 steps to complete this and a friend of yours only 2, yet you both arrive at the same and the correct answer, you'll both receive the same number of points. I will leave that up to you, as it is personal, and I will tell you that in the end you should have 2 answers for x. It's either going to be equal to 3.5 times 10 to the negative 4, or it's going to be equal to negative 5.3 times 10 to the negative 4. Keeping in mind from a practical sense that in our ICE table we had x's representing concentrations, we are going to reject the negative 5.3 times 10 to the negative 4, since it does not make sense for us to have a negative concentration. Once you've solved for x, if you're like me, you'll need to go back to the question to see what we're supposed to be doing here. And the question asks for us to find the hydronium concentration. We go to our ICE table, we find hydronium, and we notice that we said that the equilibrium concentration for hydronium was x. Therefore, H3O positive, or hydronium, at equilibrium is 3.5 times 10 to the negative 4 molar. That is the final answer for this question. Notice, however, it requires a lot more steps than if we go back up to example 7 when the check comes out to be greater than 500. Thus the reason it makes me very happy when the check does come out to be greater than 500.